Hello class, so first off, you hopefully did number 5 for the most part in class. Try it again without help. Come back here for help. 6 is definitely a challenge. Do attempt it on your own. Draw yourself some free body diagrams, and then I'll go over it on here. Alright, so first off, there should be a free body diagram. This is our car. This is the force of gravity. Since it's not falling to the ground, there's a normal force. The students are pushing it, but it is not going very fast due to friction. So the combined force, you can see, has to be equal to the force of friction, which we can find. We do need the normal force, which we can say, oh look, the normal force and the force of gravity will be equal. This will be 10,000 kilograms times, that's their mass, times gravity, which is 10 meters per second squared, roughly. So this will be 10,000. So our normal force will be 10,000. Our mu is 0.5. So half of 10,000 is 5,000. So they have to push it with a combined force of 5,000 newtons, so about 1,000 newtons each. That is A. Note, remember it says constant speed. That means these are all unequal forces. Alright, B. If it takes them 8 seconds over a distance of 4 meters, this is where we have power is equal to work over time. We know work is equal to some force times a distance. So we can just plug this whole thing in for the work. So power is equal to our force times distance over time. We know our force is 5,000 newtons. The distance is 5 meters. Luckily, they don't have to go too far. And the time is 8 seconds. 8 seconds to plug this all in. And you'll get 3,125 watts. Alright, then ask how much thermal energy is generated. The math is actually less hard. I will write it out. This is the idea that the heat plus the work is equal to the change in energy. Essentially, it starts out with no energy, and it's going to end with the same amount of energy, so there's no change in energy. It's still going the same speed as it was at the beginning. So we know that heat must then be equal to work, except opposite. So basically what you really want to do is find work. We essentially already found work over here. That's our force times the distance, which is equal to our 5,000 newtons, times 5 joules. Alright, moving on to 6. Try it first, and then come back. Alright, so Lisa Simpson is dragging a 100-kilogram cart full of science equipment across a frictionless, oh, that sounds important, floor with a force of 500 newtons at an angle of 37 degrees. If the cart starts from rest, and she drags in a distance of 6 meters, how fast will the cart be moving in the end? So this is definitely challenging. You're going to have to bring in lots of different parts. First off, we need to figure out essentially how much energy she's giving it. That's our end goal. Because we want to figure out how fast it'll be moving. Talking about energy, this is what we want to get to. But we need to figure out our energy first. So, in the beginning, it's got 0 energy. At the end, it's going some amount of speed, we're not sure, but it definitely has kinetic energy, so we've added work. We need to figure out how much work. To do this, work is the force that's parallel to the distance. So if she's pulling at a 37-degree angle, not all of it's parallel. So this is the part where it's especially tricky. So if we draw a free body diagram for our cart, she's pulling it at a 37-degree angle with 500 newtons. We need to figure out how much this is. So this is where we have our sine, our SOHCAHTOA, sine, cosine, and tangent. Since this is an adjacent side over hypotenuse, where we want to do the cosine of 37 is equal to x over our hypotenuse, 500 newtons. So you're going to want to plug that into a calculator to find x. So that's 382.7 newtons at that particular angle. So now we essentially no longer care about this. This is what we're going to care about. That is our force. That goes into here. So work is equal to our force, 382.7 newtons, times our distance of 6 meters, which gets us roughly 2,296, no decimals, the numbers are quite big enough, joules. So that's the amount of work we've added. So you can think, how much energy do I now have? Well, that's how much energy I now have. So at the end of it, we know it has this much kinetic energy. So we can plug this in, we know how heavy it is, and then we can figure out our velocity. So 2,296 joules is equal to 1/2 m, that's our 100 kilograms, times our v squared. This gives us 50 kilograms times v squared. Do some algebra. Divide by 50 on both sides. And that will be 45.9 equals v squared, square root of both sides. And you get the velocity to be 6.77 meters per second. So that is how fast the cart will be moved. Side note, since you know the cart starts from rest, that's how you know that this is 0. I realize I might not have explained this. So to summarize, this problem is a combination of your work as well as your different angles. Make sure you're doing it in the parallel. So to get the parallel, you have to do the SOHCAHTOA. Since we had 0 energy to start with, all of our energy at the end is from the work that Lisa Simpson added to it. And then from there we can find the total kinetic energy at the end. And from there find the velocity. Alright, hopefully this was helpful. We will continue practicing these tomorrow. Remember to do your project. So that's 3 sources was yesterday. So by Friday, you're going to need 5 sources. We will be in the computer lab, or in the library on Friday to help you get those 5 sources.